Okay, so sorry. So Mike Hansen's going to give the next stage seminar on combinatorial algebras, which are something he's implemented in Sage recently. So he's going to tell us what they are and what you can do with them in Sage and where he's going with them. And he's also giving a talk on Wednesday, actually 2 talks on Wednesday, in the combinatorial seminar. So there's going to be a pre-seminar, and which is aimed at students primarily, and then a main seminar I think at 4 o'clock.
Yeah.
Yeah, which is aimed at, I guess, a lot more. So the main seminar is going to be about combinatorics in Sage. Thanks.
Okay, so probably over the past, I don't know how many months, maybe probably about 7 or so now, ever since Sage Days 3 that was held at IPAM in UCLA, I've been working on doing combinatoric stuff in Sage. Originally, most of the combinatoric stuff in Sage was done by David Joyner, and it primarily just wrapped functionality found in GAP. And so, like, the basics were there, like permutations, combinations, and all those things, but it didn't have, well, what I consider like a particularly nice interface. So if you want to count the number of combinations, there's like a single function called number of combinations, and so on. And so I'm going to talk a bit today about like the new combinatoric stuff I've done in Sage, and these things called combinatorial algebras. So as a brief overview of what I'm going to talk about today, I'm going to talk about these things called combinatorial classes, which are just sort of a vague term that we'll use we consider them like any set of combinatorial objects. So I'll give a definition of them, some examples, and show you how to create new ones in Sage. Then I'll go over combinatorial algebras, like what they are, give a few examples of them, and show how to create new ones within Sage. And then finally, toward the end, I'll talk about symmetric functions, which is where I've been spending most of my time recently with my work in Sage, and show you what they are, and like they're an instance of combinatorial algebras. And then I have a bit of things like sort of where I'm going, things I've left to do, and things I want to do, and things I wouldn't mind people helping me out on. So what is a combinatorial class? So it's just a set of objects which one would like to ask certain questions. So this can include like all sorts of things you could consider a combinatorial class. But some of the questions that we would like to answer are, well, if our combinatorial class C, so in this example, I'll let it be all the partitions of the integer 3. Okay, so what might we ask about this combinatorial class? Well, we could ask how many objects are in this class. And so for the partitions of 3, there are 3 of them. Or what are all the objects in this class? So you can call c.list and get a list of all the objects. You can check whether or not an object is in this class. And so here you see the list 2.1 is a partition of 3, while the list 2.2 is not. So the objects in this class have some order, just the order they happen to be in the list. And so you can ask, what's the first one in this list? And so it's the partition 3. Or what's the last object in this list? Or what position is 3 in the list of things in this class? And finally, what object is in position 0? So you give it 0, it tells you which partition that corresponds to. And you can generate random elements of this class. So the idea behind combinatorial classes in Sage is that it provides a standard interface for dealing with these combinatorial objects. You can have much more complicated combinatorial classes. So for example, all of the permutations of 1 through 4 that avoid the pattern 3, 1, 2. And so like before, it would be kind of difficult to, like if we had like one function for all of these things for all of these certain combinatorial classes. So we just come up with a sort of standard wrapper, and we can access all of them in this manner. So some of the combinatorial classes that I've worked on and put in Sage, you have permutations, like all sorts of tableau, if you're familiar with what those are, combinations of like lists, integer partitions, compositions, combinations, integer vectors, which are just a list of integers that satisfy certain properties. For example, like the sum to n, but maybe like they never increase more than 2, like from one spot to the next. Linden words, necklaces, thick words, like all of these things are in Sage, and there's combinatorial classes, so you can do all of those operations that I went over before with them. So I've put a little Sage worksheet for all of you who have internet access or access to Sage. If you go to http://mwhansen.org/sage-uw.html, there will be 4 different links for Sage worksheets, and so I'm going to go over like the first one now. I'll also just do the demo here on the screen, so if you want to look at that. So those are just text files corresponding to the worksheets. But if you go to sagenv.org, I also have them shared.
This one.
And eventually we will see it. Can everyone read the font, or should I make it bigger? Is that better? Okay. Okay. So the first thing I have here is like all the permutations of 1 through 4. And so the way they're written is in like a list notation. So this means this is the permutation that said 1 to 4, and then 2 to 3, and 3 to 2, and then 4 to 1. And like before, you can do all of the operations that I mentioned with these. So if I change it to count, there are 4 factorial of them. You can also get like a list of all the permutations of 4 that avoid this pattern 3, 1, 2. So what that means is that there's no subsequence in here with relative order like 3, 1, 2. So you'll never see like something that's big and then small and then one in between in that order. So for standard tableau, I don't know if you're familiar with these, what you have is you want to think of boxes in a corner. So for the standard tableau of 3, I'm going to have 3 boxes, and gravity sort of goes up and to the left. So I may have my 3 boxes like this, and the standard tableau of this shape are all the ways I can fill in these boxes with the numbers 1 through 3, so that it's strictly increasing in the rows and strictly increasing in the columns. So here's one way, and that corresponds to this one right here. Or if I have a different shape, like where there's 2 boxes on the top and then 1 below, I could fill it in 2 ways. You could do 1, 2, 3, or you can do 1, 3, 2. So those are standard tableau, and they come up in when you look at, say, the representation theory of the symmetric group. You can also do semi-standard tableau, which are the same sorts of objects, but where you only have to be weakly increasing in the rows and still strictly increasing in the columns. I could also get all the standard tableau of a given shape. So this should be just those two that I talked about before. Standard skew tableau are like this, except I take out some boxes from the corners. And I still have, they still need to be strictly increasing in the rows and columns. So right here, these are the standard skew tableau of shape 2, 2. And there's an empty box in the upper left-hand corner. So those are all the standard tableau of that shape. You can go on, you can get combinations. It handles combinations. So here, it'll handle cases where you have duplicates, and it'll handle them correctly. So this up here corresponds to all the ways you could pick all the ways you could pick a subset of that. So you have the empty set and so on. And here, if you look at the case where you pick two of them, you'll notice that there's only two combinations because the ones are duplicated. So like before, it would give incorrect results. It would show all three different ways. And so there's next are the partitions, integer partitions of 4. So that's all the ways we can write 4 as a sum of non-negative, like sum of positive integers, such that they're weakly decreasing. So these correspond to like the shape of those boxes. Skew partitions are similar, where the first entry here, like 2, 2, 1, corresponds to the shape of the outside partition, the boxes, and the 1, 1 corresponds to which boxes you take away. I don't think I'm going to go over anything more, but there's lots more examples of all these sort of things that are in Sage now and you can work with. So one of the things that I wanted is to make it able for users to create like new combinatorial classes, like on the fly or just like within the notebook. And so as you saw before, there's lots of functions that you have to implement to have like a full combinatorial class. But we should be able to just have default implementations of all of those, so that all you really have to implement is enough functionality to like completely describe the class, and then all of the other stuff will come for free through default implementation. But these implementations will probably be a bit more inefficient than if you wrote specialized ones for your class. So these are 5 different ways that you can specify the elements of a combinatorial class. So you could implement the .list method and just return that list. And so if you do that, then rank, unrank, count, all of those will come for free. Or you could implement an iterator in Python that yields one element of the class at a time. Or you could give it an unranked function, and then, or first you could say what the first element of the class is, and next would take in an element of the class and spit out the next one. Or you could give last and previous. So like once you implement one of these, you get the full range of functionality associated to a combinatorial class. And so that's really helpful because like a lot of times if you're going to be working with combinatorial algebras, which I'll show you later, you'll want like all of these to be there. And some of them, like the default implementation is the best you can do. So there's no reason to write that 100 times for like 100 different classes. So I'm going to show you an example of how you would write a new combinatorial class corresponding to binary vectors of length n. So this is just the class of all, say, Python lists, where each element of the list is either 0 or 1. So we could do it in the following way. We could specify the first binary vector, which is just the all zeros one. And then we could implement a next function. And how you do this is you say, find the first 0 in the list, and then replace this initial sublist, right, because here's the first 0, with this one. So if you pull up the binary vectors worksheet, you'll have an example implementation of this class, which I'll show you here in a second. Okay, so here's a sort of rough implementation of this combinatorial class. So the first thing you need to do, which sort of makes it all work, is subclass combinatorial class in Sage. And so I just define an init method, which specifies the length of the list, a repr to say, well, what the combinatorial class is, contains, which is how I do type checking. So if I pass it an object x, how do I check whether x is a binary vector of length n? Well, I check that the length of x is the same as self.n, and every element in x is in 0 or 1. And so here I define first, which I just return the list 0 times the length, and then next I find the position of the first 0, and then what I do is return that sublist, or that sublist I specified before, where you have this number of zeros, then a 1, and then the previous list. So once I do that, then I can create an instance of this combinatorial class. So I'll call it BV3. And so it's all the binary vectors of length 3. And so we can check like whether or not something's in that class. That is slow. There you go. We can list everything in that class. So here is all the binary vectors. We can count the number of them. We can iterate through them. We can do unranking by indexing this combinatorial class object. We can also use the unrank function to unrank. And let's see, we can rank. We can generate a random element. We could get the first one, we could get the last one. And we get all of this functionality just by specifying the first and the next function. So it makes it like very convenient to implement these, especially if you're doing a lot of them, or to quickly implement them. Okay, so now I'm going to talk about combinatorial algebras. which are objects that I'm interested in. So first, I'll give a definition. And a combinatorial algebra is a module, or like a vector space, over some base ring that has a basis which is indexed by elements of a combinatorial class. So for every element in the, or object in the combinatorial class that we saw before, we'll get a basis element of this module or vector space. And this algebra has an identity element. So one of these combinatorial objects corresponds to an identity on this algebra. And then you also have a multiplication rule. And it's typically defined by some like combinatorial process involving the objects which index the basis. So it's probably easiest to look at some examples and get a sense of what these things are. The symmetric group algebra of order n. So these consist of linear combinations of permutations of size n. So the combinatorial class in this is these permutations. B1 corresponds to the identity permutation, which is just 1, 2, 3, 4, all the way up to n. And you do multiplication in this algebra by just multiplying the permutations. So if you think of them, if you think of permutations as bijections, then the multiplication is just a composition of those bijections. Another thing you may remember if you are at Sage Days 4, here are Schubert polynomials. So this is a combinatorial algebra where the underlying combinatorial class is all permutations. So we don't fix a certain length. The identity permutation, is the one in this algebra. And multiplication is given by something called Peary's rule. It turns out these polynomials form a basis for a multivariate polynomial ring. And so it's actually an open problem how, given two permutations corresponding to Schubert polynomials, like how to multiply them. And it's been an open problem for a while. And so the way you multiply them is you take one of these Schubert polynomials, like expand it in terms of monomials, just say like x1 squared plus x2, and so on. And then there's a rule for multiplying each of those variables by a Schubert polynomial. Free Lie algebra. So I don't know if you're familiar with Lie algebras, but the combinatorial class here is related to these Linden words. And the one in this is just the empty list. And multiplication or forming a bracket in this Lie algebra is given by bracketing. So it's kind of interesting that you can view like this free Lie algebra as a combinatorial algebra. And then symmetric functions, which I'm going to talk about later, is a combinatorial algebra, and where the class is given by integer partitions. So those are like the sums representing a number by a sum of positive numbers that are weakly decreasing. The one in this algebra is given by the empty partition. And well, multiplication turns out there are lots of different bases for these symmetric functions, and depending on which basis you're in, then the multiplication rule is different. But they're all based on what integer partitions you're working with. So I also wanted to make it easy to define like new combinatorial algebras in Sage, because, well, combinatorial algebra is just sort of a generic term that can like encompass a wide range of things. Like, say you have any finite dimensional algebra, then it has some, you can pick some basis for it, and you could form a combinatorial class out of whatever that basis is. It may not be particularly interesting, but if you do that, then you can view that particular algebra as a combinatorial algebra. So, yeah, so before, to create new algebras in Sage, you have to subclass both the algebra class and the algebra element class for the elements of your algebra. You have to sort of choose the underlying data structure in which to implement this algebra, and then implement like a fair amount of boilerplate functionality, which is relatively common to sort of all of these combinatorial algebras. But it should be like easy for new users to create these combinatorial algebras, just because they're it's pretty easy to come up with a new one, or yeah, there's just lots of things that you may want to do. And so I'm going to give an example of how you would go about creating a new combinatorial algebra within Sage. And the one I'm going to implement is called the Q shuffle algebra. And so this algebra has connections to, say, theoretical physics and these things called quasi-symmetric functions. But it's pretty easy to define. Sort of the combinatorial class underlying this algebra are words. And by this I just, well, in Sage, I just mean a list of things. You could specify words from some alphabet, but here I'm just going to go with words. The identity element in this algebra is the empty list, and multiplication is given by this thing called the Q shuffle product. So I'll go over what this is. Okay, so we define the Q shuffle product between two words recursively. So here, if you take the product of the empty list with the word, it doesn't matter which side you do it on, you get that word back. So it is indeed the identity. Now if you have two words here consisting of U, which will be a word, and then A, which will be like a single letter from the alphabet tacked onto that. So the size of this word would be the size of U plus 1. If we multiply that by this word, BB, then how are we going to define that? Well, what we do is we take the shuffle product of UA and just V. So we take off the B from the list BB, and then compute this shuffle product. And then once we've done that, what we do is we take B and append it to the end of every word that shows up here. Then we add that to this number Q, or variable Q, raised to the length of BB. And then we do sort of the other way, where we take A off of U, compute the shuffle product, and then append A back onto U. So eventually, once you, when you go to compute these things, since you're picking off one every time, eventually you'll get down to this case. So how do we go about implementing this in Sage? So if you go to the worksheet called Q shuffle algebra, it'll have the implementation of this algebra. Okay, so there's a couple parts to it. The first thing is the init method, where we take some base ring R, and we set the combinatorial class of this algebra. Here, it's just going to be words. So this corresponds to some combinatorial class object in Sage. The name of it is going to be the Q shuffle algebra. This is the one, like we talked about before, the empty list. When we print elements of this algebra out, we're going to prefix them with W, just so we can recognize them. I'm actually going to make the base ring, the polynomial ring, the univariate polynomial ring in the variable Q over this R that was specified. And self.Q is going to be the generator for that univariate polynomial ring. And then we just call the parent or superclasses Init Method. Okay, so here's the implementation of the Q shuffle product. So the very first part is if either of UA or VB is the empty list, then we're just going to return the other one. Note what I'm doing here is I take VB and make sure it's a list, and then pass that to self. So this right here is actually an element of the Q shuffle algebra, and not a list. Okay, so if VB is 0, I do the same thing. I just return the element corresponding to UA. If neither of those hold, then what we have to do is the recursive step. So U is just this list, but we chop off the last one, and then we set A to be the last thing in that list. Similarly for B and B. So the first term in that sum I showed was we multiply UA times B. And the second term in that was we multiply U by VB. And then what we do is that sort of append step, where we take the first and append on B to every word in there. And then we have self times raised to the power of length VB times the second word, well, the second element with A appended onto the end of that. And then we have an implementation of the append. Right now it's pretty messy because I don't have any methods right now for working with the objects in the underlying basis. But hopefully shortly that will change and you can get a much cleaner implementation of this. This just sort of works with the underlying data structures that it's using. But all this does is take every basis element, or in element, and appends X to the end, each of those. Okay. So with that, I've defined this new algebra in Sage. So I'm going to turn on logic print. Okay, so here I'm making W, which is going to be an instance of this algebra. I'm going to define variables A, B, C, and D. I guess they're already there. So here, this is a word with like letters coming from the alphabet 1 and 2. And so what we can do is we can, this corresponds to a basis element. So we can compute the element of the Q shuffle algebra corresponding to that, and then 2, 1. I'll show you if we do append to this element right here, we just get 1, 3, and then 2, 1, 3, like you'd expect. So here's an example showing the multiplication of these elements. You get, if you take the Q product of 1 and 2, you get 1, 2 plus Q, 2, 1. And you can do like fancier computations with these. You can have this, so it doesn't matter where the letters in your alphabet, or letters in your word are coming from, it'll handle them correctly. So here we take the Q shuffle product of BCD and then 2, 3, and you get this fairly complicated expression. And it works with all of Sage's coercion, so you can multiply things by a half. Here, when we do 1 plus W 1, 2, what it'll do is it knows that this can coerce into the base ring of this algebra, and it will form like the correct element. So if I do, say, W of 2, it knows that that should be a scalar multiple of the identity element. I need to fix like the LaTeX printing because it's not showing like the brackets of the identity. But so with, I don't know how many lines of code that was, not a whole lot, something like 20 or so. You can define this like whole new algebra, work with its elements. You can let's see. And there's also like functions for these elements. So like I think but you can say like get the support of this element, which corresponds to all of the combinatorial object elements with non-zero coefficients. So there's a list. Here's a list of the objects corresponding to the basis, and then these are the coefficients on that. So it makes it, for a lot of things, like having this generic combinatorial algebra class, it makes it easy to implement a lot of things. For example, I did this symmetric group of order n, and that only takes maybe 10 lines to do. And then you can do like all these computations with it, and it's pretty nice. Especially compared to like what you had to do before. There's a lot of stuff that you had to implement to get a new algebra. Okay. So now I'm going to talk a bit about symmetric functions, which is, as I said, where most of my work has been recently. And to start off, I'll give a definition of what symmetric functions are. So what we do is start off with symmetric polynomials. So a polynomial of some multivariate polynomial ring, say in n variables, is said to be symmetric if it's invariant under any permutation of those variables. So say we have some multivariate polynomial, and we swap all of the x2s with x3s. Okay, if we do that and get the exact same polynomial for any permutation, then we call it symmetric. So some examples of these are, say, x1 squared plus x2 squared plus x3 squared. Right? We can swap any of the variables and we still get the same thing. Or we can look at, say, all subsets of size 2 of the variables. If we swap anything, we'll still get a subset of size 2. So this is symmetric. Or you could look at all the sum of all the monomials of degree 2. If you swap any of the variables, you'll still get a monomial of degree 2. So this function is also symmetric. So a symmetric function is a quote-unquote polynomial in infinitely many variables. So you have like a polynomial ring with infinitely many variables. And so the symmetric function algebra, which is typically denoted by uppercase lambda, is the algebra with these symmetric functions as its elements. So if we want to do computations in an algebra, you typically want to have a basis. And so there are several nice bases for the symmetric function algebra, and all of these are going to be indexed by integer partitions. So here are some examples which you've probably seen before. And so for every integer partition, you get a basis element of a symmetric function algebra. So I'll go over what some of these bases are. So first you have to power some symmetric functions, which is what you saw before. And we define p sub r, where r is just a positive integer, to be the sum of just x sub I to the r for all of the variables. And then if we have an integer partition lambda, so that's just a list of positive integers, what you do is you just take all the elements of that list, find the corresponding power sum symmetric function, and then multiply them all together. Because this is a commutative algebra, right, we're just pretty much working in some big multivariate polynomial ring. It doesn't matter which order you do the multiplications, and so that way you get integer partitions because you can organize them from biggest to smallest. So here in Sage, I'll define P to be the symmetric function algebra on the power sum basis over QQ, so the rationals. And what I can do is I can form the power sum symmetric function corresponding to the integer partition 2 and expand it on 3 variables. So this is what I would get is if I chopped off all of the terms involving variables higher than 3. And so what we get is x0 squared plus x1 squared plus x2 squared. If we define a to be the power sum symmetric function corresponding to this integer partition, and we expand it on 3 variables. Or what we could do is take the power sum symmetric function corresponding to 2, expand it on 3 variables, multiply that by the power sum symmetric function expanded on 3 variables. And what we see is that these are the same. So this this up here is the element of the power sum symmetric functions. And this here, like the multiplication is taking place between multivariate polynomials. So you can see that this sort of corresponds to the operation that you think it would. The next basis for symmetric functions are called the elementary symmetric functions. So we saw these before. What we do is define e sub r, where r is a positive integer, just to be the sum of all subsets of variables of size r. And then like before with the power sum symmetric functions, this is, these are known as multiplicative bases, because what you do is if you want the one corresponding to an integer partition lambda, what you do is you just take all the e sub r's corresponding to those parts and multiply them all together. So here we can create the algebra in this basis by running this command. And then if we look at 2, e sub 2, and expand it, here you see all possible subsets of 2 variables from 3 of them. And you just sum them all together. You'll see like all these are symmetric polynomials. But you could do this for any n, because these are defined for like infinite polynomial rings and infinitely many variables. The homogeneous symmetric functions, h sub r is defined to be the sum of all monomials of degree r. And again, we define h sub lambda to be the product of all the h sub lambda i's. So to get this basis, you do SFA homogeneous. And here we can expand it on 3 variables, where if you look, every single monomial of degree r is represented here. Then we get into a bit more interesting bases, the monomial symmetric functions, which are denoted m sub lambda. And what these are these are the sum over all the orbits of x sub lambda. And so what do I mean by that? Well, say you have some symmetric polynomial, and you know that x1 squared times x2 is like a term of that polynomial. Because this polynomial is symmetric, then if you interchange any of those variables, that also has to be a term there. So if x1 squared times x2 is a term, then x2 squared times x1 also has to be a term. So you take x sub lambda, which would be some variables, and then with the exponents as the parts of lambda. And you just act on that by the symmetric group, like interchanging variables, and you'll get all these terms, and then you just sum them together. So here, if we look at 2, 1, and we expand it on 3 variables, what we see is x0 squared times x1. So here's the power of 2 corresponding to that, and here's the power of 1 corresponding to that. Well, if x0 and x1 are there, we should be able to switch them, because this has to be symmetric. So we see where is it? Yeah, x0 times x1 squared. Or you could swap the x1 with x2, and that'll appear there. So these are the monomial symmetric functions. Like I said before, these are over infinitely many variables, so you can like make that as big as you want, and it will give you the expansion. And then finally, we have these things called the Schubert symmetric functions, and they're a bit more interesting. What you have, s sub lambda corresponds to the sum over all semi-standard tableau of that shape, and then x to this t, where t is the tableau, and I'll show you what that means. So for 2, 1, here is the shape corresponding to 2 and then 1, and these are the 2 semi-standard tableau, where we fill it in with 1s and 2s, and it has to be weakly increasing on the rows, strictly increasing with the columns. So these are the 2 ways to do it. And so how to go from a semi-standard tableau to a monomial, what you do is you look how many 1s are there in that tableau, and that's the exponent on x sub 1. And then how many 2s, or if we do this, there's 1, 1, and there are 2 2s. And so you can get these Schubert functions in Sage by using the SFA Schubert command. And if we expand it on 2 variables, then you get what I showed above. Okay, so we have all of these different bases for the symmetric function algebra. And you can do all of the computations in each of these bases. But you also, like some of the, I guess I'll talk about, there's also a scalar product on this algebra, a pretty standard scalar product. And we define it by the following relations. So if you have a power sum symmetric function corresponding to lambda and one corresponding to mu, and then the scalar product of these 2 symmetric functions is defined to be c sub lambda, which I'll talk about in a second, times delta of lambda and mu. So if lambda and mu are not the same, then the scalar product is 0. Otherwise, it's given by z sub lambda. And this is defined to be the centralizer of a permutation of cycle type lambda in the symmetric group. So it's not particularly important what that number is. It's just that the power sum symmetric functions are orthogonal. Like it's an orthogonal basis under this scalar product. So here, I take the partitions of size 4 and then map them all to the size of the centralizer of a permutation of that type, you'll get 4, 3, 8, 4, 2, 4. So these are the values that are going to appear here when lambda and mu are partitions of 4. So if we have a scalar product on the symmetric function algebra, and we have 2 bases, A and B, we say that these bases are dual bases to to each other with respect to a particular scalar product, if and only if the scalar product of A lambda and B mu is just delta B mu. So the power sum symmetric functions are not quite self-dual because they have that factor of C there. But it turns out that we have the following dual base pairs with respect to the scalar product I talked about earlier. So the Schubert symmetric functions are dual to themselves. The monomial symmetric functions are dual to the homogeneous ones, and the elementary symmetric functions are dual to these things known as the forgotten symmetric functions. And they're called forgotten because no one ever works with them or like talks about them. But it turns out that they're the ones that are dual to the elementaries. So if I have, say, the monomial symmetric functions in Sage, and I call it dual basis, and so if you don't call it with if you don't put a scalar product in here, then it just defaults to the standard one. So the dual basis, the monomials is the homogeneous symmetric functions. So there are a number of things that one would typically want to do with symmetric functions, or in a symmetric functions package, is do, say, change a basis. So if we have some symmetric function like the power sum basis, like how can we convert it into the Schubert basis? Or do multiplication within this algebra. As we saw for the multiplicative bases, the elementaries, the power sums, the homogeneous ones, multiplication is really easy. All you do is take the two partitions, like concatenate them, and then sort, because it's a multiplicative basis. But for the Schubert symmetric functions and the monomial symmetric functions, the multiplication is a bit more involved, and especially in the Schubert symmetric functions, the coefficients of the symmetric functions that appear in the product, it's given by something known as the Littlewood-Richardson rule, and it's a pretty well celebrated result and has analogs that appear elsewhere. And we'll want to compute like the scalar product between these symmetric functions. And also this thing known as platism. It's like roughly the way to think of it is if you take a symmetric function and look at its expansion as a multivariate polynomial, and then for every variable, like you plug in another symmetric function. So it's kind of this composition of symmetric functions, and it turns out it's related to, you can get some interesting results in representation theory by looking at platisms of symmetric functions. So I'm going to do a little demo about the symmetric functions in Sage. So if you pull up the worksheet called symmetric functions, that will be the one I'm going over. I guess they're all there. So you can take, you can add symmetric functions. Here you can convert between, so A is in the Schubert symmetric function, and then we can convert it to the monomial basis just by calling, using the .call method. And so this is what that symmetric function looks like in this basis. You can do the same for the power sum, elementary, homogeneous. All of these base conversions are defined. You can do multiplication, as shown here. And so even with something, it seems relatively simple. A was just to be defined to be S21 plus S3. Like these things blow up quickly. And if you wanted to try doing sort of these computations by using the raw multivariate polynomials, like they just get huge once you start getting like I don't know, up to partitions around 8. It's just not very efficient to work with the raw multivariate polynomials. So here I give an example where I convert A into the H basis and then square it, or I square it and then convert it into the H basis, and you see that you get the exact same thing. I can do, here's scalar product. So here's A again, and I take the scalar product of it with itself. Well, since the Schubert symmetric functions are self-dual, then you get a 1 from here and a 1 from there, corresponding to 2. Or the power sum symmetric functions. We saw that they were almost dual, but we had that factor of c. So here we can figure out what that c is, and then that's the same thing we did here. If lambda and mu are different, then we get 0. And here, m and h are dual bases. So when we have the same partition, we get 1. Plethisms. Here, what I'm doing is I'm taking the element A and sort of composing it with itself, and you get this big expression. Since the maximum or the maximum size of all of the partitions in A was 3, A of A will have partitions of 9. So these are the partitions of 9 that appear in that plethism. So we're running a little late, and I'll finish up here. So things I want to do. So we have the symmetric functions were an example of a combinatorial algebra with many bases. In fact, well, you could define a lot more bases, and some of them are interesting to work with. So right now, all of the code for converting between these bases is in, it has to be within each of the classes corresponding to them. And so it would be nice if there's sort of some overarching symmetric function object that knows about all of these different bases and can handle, there would be one spot for doing all of these conversions. Especially when you start getting in, there are some generalizations of symmetric functions, and you can have upwards of, 15 or so different bases that you'd want to work with, and you'd want to be able to perform the conversions between all of these. And so what you don't want to have to do is, for each one, define the conversion from everything else to that one. You'd sort of want to have a big connected graph, and if you add a new node to that graph, it should be able to figure out some path to go from one basis to another. Graded combinatorial algebras. So when everything is finite, or you have a finite dimensional algebra, then you can say take an element and then represent it by a matrix, like how it acts on that algebra. But for infinite dimensional algebras, you can't really do that. But you can get some nice things if they're graded, so they have components that are all finite dimensional. So there should be a nice way to handle these graded combinatorial algebras by having a graded combinatorial class, and it knows how to do all the right things for that. There's also these things called Hopf algebras. They're pretty interesting. So symmetric functions are actually part of the Hopf algebra. Group algebras, Lie algebras, they all are instances of Hopf algebras. And so a Hopf algebra is an algebra, but it has this thing called a coalgebra. And in order to work with these, you need to be able to work well with tensor products of modules. there's a thing called a co-multiplication, where it takes that element in the algebra and sends it to an element of the algebra tensor with itself. So these are pretty interesting, and so hopefully in the near future I'll try and get like some of those. Generalizations of symmetric functions are, here's some of them. So you could have non-commutative symmetric functions. So before in our multivariable polynomial ring, all of these symmetric functions had to, well, all of them did commute. So we could look at what we get if none of the variables commute. What sort of objects do we get there? These things called quasi-symmetric functions. All Littlewood polynomials are symmetric functions, but instead of working in lambda, you work in univariate, with coefficients in a univariate polynomial ring. And then McDonald polynomials are a generalization of these, where you work with coefficients in a polynomial ring over two variables. And these, there's lots of research currently being done with McDonald polynomials. They have lots of interesting applications and have been a pretty hot topic in, say, representation theory or combinatorial representation theory. And so those I would really like to get in Sage, and especially for working with them, you can run into some computational issues because how you could define them is by, say, they're like dual with respect to dual to a sum basis with respect to a different scalar product. And so you need to do a lot of linear algebra over fraction fields of multivariable polynomial rings in order to compute what these things actually are. And that's about it. Does anyone have any questions?
How does the functionality for combinatorial algebras compare to that's available in Magma or Mathematica packages?
There's actually, Magma is good with dealing with, say, group rings or group algebras. I mean, it has a lot of functionality for that, and so those would be an instance of these. For all the classical bases I showed, all of the arithmetic and sort of multiplication, that's all done using Symmetrica, and so Magma also uses Symmetrica for handling its symmetric functions. But Magma doesn't have Littlewood polynomials or McDonald polynomials. The only places I know where there's implementations of that are John Stembridge's SF package for Maple. But since it uses Maple, it's incredibly slow. So working with these things is for a reasonable size is not really possible. The other place that I know of is MooPad. They have a lot of this stuff, and that's where most of my work has been taken, or I've gotten a lot of inspiration from that project. But I just started playing around with these recently, and one of the bases for the all Littlewood polynomials involves a lot of linear algebra over univariate polynomial rings. And so I multiplied Q of 3, 2, 1, so the integer partition 3, 2, 1. I just squared it and figure out how long it takes. So in Sage, it takes about 12 seconds to square that one basis element. But in MooPad, it took 20 minutes to do that same computation. And I mean, so what I think it is it turns out for that computation you had to invert an upper triangular matrix, so that you can do that pretty efficiently. But I think in MooPad they were inverting the whole matrix, and well, MooPad's arithmetic for univariate polynomials is not nearly as fast, and they're working with generic expressions. So for
Cool.
these sorts of things, yeah, Mathematica, there isn't really anything for symmetric functions. So I would say MooPad is probably the most fully featured, but it's slow.
Yeah, I've tried benchmarking MooPad a little for arithmetic, and it's kind of silly.
Yeah.
So let's think, Mike, if there are any other questions, you can ask them afterwards. And thank you. And I also want to point out that there will very, very likely be a Sage Days, I think 7 in UCLA that's going to be on combinatorics. So if you're interested in combinatorics, you may